Hi, everybody. Thank you so much for joining this vector search conference. In this session, I'd like to introduce you the vector search feature provided in Cloud SQL for MySQL from Google. A little bit about myself. My name is Shu. I'm currently working for Google. I'm in Cloud SQL for MySQL team with a focus on MySQL engine, vector search, GenAI related areas. Before joining Google, I had worked for Alibaba and Oracle, also in database and distributed system. So in this talk, I'm going to start with a quick overview of the vector search we implemented in Cloud SQL. Then I'll dive into the technical details, discuss the core features and designs, those fundamental ones that are tightly coupled with our uh, vector search characteristics. Then we can look into the core interfaces. I'll give a real-world demonstration and see how it can help solve the user's scenarios. As we all know, GenAI opens the door for so many opportunities to all the businesses. It is now a billion-dollar market already. And what's there for MySQL customers? The ideal situation would be that our customer they can access new GenAI features from the same place where their data has already been stored. So there's no hassle. They don't have to move around, jumping between multiple infrastructures, multiple systems, and they don't need to transfer data here and there. They don't have to make copies of their data all over the places, etc., etc. So Cloud SQL has sensed this need and has acted upon it. Our first version was made available on April 2024 as a public preview. It came with a LangChain integration, so we published blogs and collabs to demonstrate how to take this new GenAI into the production line. Our GA version was released roughly about half a year later. It was on December last year. It is a big leap, and we have tested with billions of vectors, all stored in single Cloud SQL instances and being queried for days. So after GA, we are able to roll out updates through maintenance, and we have been keep on doing that. For example, we have released Vertex AI integration on Google Next. Gives the customer the capability to access a vector generation from the Vertex AI system within the database environment. And we will talk about later in the future slides. Now let's look at how we actually did it. The vector search in MySQL. This is a very simple, straightforward phrase. And obviously there are two factors in it. MySQL, this is the context. And the vector search, this is the innovation we wanted to add to this context. And talk about MySQL, the first one. It is a traditional relational database. And in order to add new features, there are a few important characteristics that are required. First, we don't like a read-only system. We want the vector data and the vector index stay in sync and can be updated. So the embeddings changed, the indexes should change accordingly, like any other indexes. So we want to support DML. And the second, we want it to have crash safety. The vector data and indexes should enjoy crash recovery like any other database. And on top of that, we also want it to be transactional semantics appliant. So vector indexes shall support all the isolation levels and transactional semantics, same way as all other indexes. And the user can have multiple transactions. They can access the vector data, vector indexes, and with their adequate scope and visibilities. And also, equally important, the customers have the ability to import existing embeddings. We would also want them to have the capability to generate embeddings from the existing data without need to go outside of the database. So they can do everything in one place. So for our second factor, vector search, we know that the ANN query, like many of my colleagues probably have already explained thoroughly in this session, this conference, and we need a search library as its core. And for that purpose, we Cloud SQL picked the scan library as the search engine. Scan came from Google. It has been powering so many Google products for years, such as ads, YouTube, etc. All these planet scale Google products have made Scan a tested and proven solution, especially for large data, as you can imagine the scope and the high throughput. And at its original form, Scan is an in-memory library. So here is the caveat. We cannot directly adopt Scan to MySQL and drop it, and so be it. We need add a traditional OLTP support, which means we need to add capability for mutation. We want it to have crash safety, and we want MVCC. So in order to make these enhancements, MVCC, crash safety, etc., we want to first understand how Scan works. At its core, Scan is a k-means partition. So giving a number of vectors, the Scan will first train with the training data, which will compute centroids, the partitions. We also call it the leaves. Their centers are called the centroids. After training, actual data are dropped into each leaf partition so that we have a search tree. The vectors can be quantized or in different ways or hashed. In this case, in Cloud SQL, we use Scala quantization. That's why you later will see that we call our tree type as tree SQ. So after the index tree is built, like this shape, and when a query comes, the Scan will first compare the distance of all the centroids and the query index to find a set of leaf partition that are close enough to this query index. For example, here I have a query index. Okay, I picked two very close centroids. Then the Scan will search all the data points only within those selected leaf partitions. Therefore, we can limit our search range to a very, very small percentage of the overall data set. And that makes Scan that fast. All right. So now we know how Scan works and we know our database requirement. We can see the centerpiece of vector search design is to model the Scan object, the Scan k-means partition, as a standard database index. So the structure of this index should be able to map the base table rows where the actual vector embeddings are stored to the k-means partitions that we just discussed. And this gives us the capability to increment persisting the index whenever there's changes, because the change will reflect to local partition change. And to achieve transaction and isolation, the index change need to be bundled together with the base table change in the same transaction. Therefore, we can achieve MVCC and also will have the crash recovery capability thanks for the existing infrastructure from MySQL. The storage media is another interesting topic. We know logically the scan partition is modeled as an index. Well, to be exact, it's a secondary index because there's concept of mapping the base table row, the PK, and the partitional information, the leaf partition. However, we know this vector data are also quite large with thousands of dimensions possibly. So the normal secondary index data structure has a limitation on the data size. To solve this problem, we made an innovative design. We use a normal table to persist index data. So on storage, it looked like a table, but at upper level usage, it is a secondary index. With that, we have no limitation on the data size, and this table structure is flexible enough for any future expansions. Okay, based on that, here is our storage architecture. So we have the scan library, and then it helps us to maintain a vector embedding in a base table. This is stored in a traditional DB table as var binary columns. And then the Sky library is used to create and search the vector indexes. And we have this vector index object that utilizes the scan library, and it has a couple more building components. The mutator is used to sync up the change between vector embeddings and vector indexes. The searcher is used to search to serve the queries from the SQL layer. The builders takes care of training and index creation process. There is a shared component called persistence. This is used to persist any changes from any component down to the subtable that we just discussed. So this subtable look like a expanded secondary index like we just talked about. It has partition data, it has the base PK, and it also has some additional vector data that can help facilitate our searches. Another shared component is called memory regulation. This one helps us to make sure the vector search does not occupy too many memories. We know that MySQL has a buffer pool and other memory usage. In Cloud SQL, the memory is already allocated delicately. We don't want to break this beautiful theme. So we have this memory regulator, and customer can say how much memory shall be dedicated to vector search, and we'll follow that. And go above the layer. To help the vector index model works with all other existing components in MySQL, we add new field in the table structure, this one, the green one, and to indicate that this table had a vector column. And accordingly, we also add new field in the index data structure, the blue one, to indicate that we have a vector index on it. With these two information, the SQL layer should be able to discover the index and utilize the index when necessary in the search. Of course, all these requires a InnoBase handler for SQL layers. Another important one is the capability of generating embeddings. So basically, for a customer, they want to compute embeddings directly from the SQL databases, from MySQL. And they don't want external pipelines. They don't want to move their data out and back in. They don't want all these hassles. But in reality, many of these features are now available in a different AI or ML system that is totally a separate identity other than the database instance. So for one example is Vertex AI. Google provide this Vertex AI system, and it has the foundation models and tools to tune these models. And it is a very sophisticated system. Customer can access all these models or even their own models. So our Vertex AI integration bridge the gap between Cloud SQL instance and the AI ML system. It uses a user-defined function to transform a user query to a REST requirement from the Cloud SQL MySQL instance to Vertex AI, and then get the data back, and then update the table. With that, a customer can just use a SQL statement to get online prediction from models hosted in Vertex AI. Okay, I have introduced our storage design, our Vertex AI integration. Here is a summary of the vector search implemented by the Google Cloud SQL. So there are a few things I want to highlight. First, for the size limitation, we actually don't have any limitation. Our design is quite flexible. We have a very smart way of using the memory. So in fact, we can support millions and billions of vectors in one single instances. Well, as I earlier explained in our GA version. So we actually can support as many vectors as you can store in this instance. Our storage is on disk, of course. We have crash safety, and also we have full transactional support. We have full MVCC. And because of that, we don't need to reload or rebuild the index at startup. We can just reboot the machine and start using this index, as any other indexes. And we also have the capability to generate vector embeddings through Vertex AI. Our DDLs and also DMLs are all regular standard SQL syntaxes. The existence of the vector indexes are aware by the optimizer. Therefore, the optimizer can choose ANN or KNN depending on the cost model. Okay, now with all these technical details, now we can see how we can use this system in a real scenario. All right, enabling vector search in Cloud SQL is quite simple. There is only one flag to control the whole feature. It is called Cloud SQL underscore vector. So I have a screenshot on the left-hand side. This is a web page when you create a database, and you can do the same while the database is created. You want to modify it. Basically, on the flag, we have this flag. You add it to turn it on, you are good to go. And there's another optional flag for the tuning. So without touching anything, this flag, Cloud SQL vector max memory size, is automatically configured according to the machine type. So if the machine has more memory, then we'll accordingly allocate a little more memory for the vector usage. But the customer can always customize it. So say you have a huge data set, or your data set has like so many dimensions, and then you can compute how much memory are required. The peak requirement always comes from training session. So you don't have to really particularly work on the use, like search cases. They only take a very small amount of memory. But in order to make the training go smoothly, or for example, you want your training to have more sample data, that also works. So you can customize that, how much memory would be able to fit the training peak usage. So after enabling the vector search features, then we can try it out, play around, and see how it works. So here, imagine we have an e-commerce scenario. Let's say I'm trying to build a product recommendation system. for toys. And now I need my table first. All right, I can create the table with vector embeddings in one go. With this syntax, it's a standard create table syntax. We just added a new data type called vector. So it has dimension to be specified a similar way like varchar or the other ones. And it is actually a shallow type. Under the hood, it is a var binary. So the syntax says using var binary. Or if the table has already been created, like the second case, and then we can add a vector column to it. We use the standard alter table add column syntax, again, the new data type vector. So after we have the table in shape, and then we can try to load the data. We can just load them all at the same time. For example, if we don't have the vector embeddings before, we can call our ML embedding function, the one that being introduced for the Vertex AI integration. We can call this ML embedding function and provide a model name and say which column to be used for the prediction, and then use the output to update the embedding column. And then we shall have the table fully populated with the vector embeddings generated by the Vertex AI. Or some customers, they already have their embeddings somehow generated from other systems, and then we can insert it into the new MySQL table. So it's a standard insert, and we use a function string to vector to change the text representation of the vector to the var binary that being used for this vector embedding storage. And in this case, let's say we added Squishmallow. It happened to be my daughter's favorite toy. Okay, so we have the data. Now we can create the index now. So we need enough embedding to create the index. The minimum number is 1,000 embeddings. Without embedding, we can also do query, which is called KNN, but it will be significantly slower. So for this case, let's assume we do want to create the index. So our create index syntax is quite standard. It's a create index syntax, but we add a keyword vector here as well. So we say create a vector index. And there are a couple options. Using scan is the default. We don't have to say it. Quantizer equals SQ, Scala quantization. It's also default. The one mandate option is to specify the distance measure. And let's say we use cosine this time. So after the index is created, we can also drop it the same way, just like dropping any other indexes. And to follow the existing standard, creation and deletion can also be done through alter table statements, like I have demonstrated before down here. So after we have the index, now we can do the queries. With the index, we are able to do the n and nearest neighbor search. It is indicated by the function approximate distance. This function tells the SQL layer that the user wants to do an n search against the index vector index table created on this column and the query vector and the distance measure. This function, approximate distance, can be used in two places. One, it is in order by clause, and as I explained here, so we can say select all these toys and order by the similarity and of one search query, and I want to 10 result. We need to have a limit clause for order by situation. And it can be also in a select list. So we can select the approximate distance Therefore, the customer can actually get the distance value, and they might be able to do more processing use these values. For example, giving a threshold, and they wanted the distance to be selected only if it is above a threshold, for example. So not just ANN, uh, Cloud SQL can also do KNN. Well, KNN, as we said, it's slow because it's brute force, but it is also it's the most accurate because it scans all the table. So in the situation where you have little data, you just want to try it out, KNN is a good option. So to specify KNN, we use a different function. This function is like the not approximate distance, but it's some exact distance. We can have cosine distance here. And if you read the manual, we can have other ones like L2 square distance, etc. So if we have a select of the cosine distance of the above data set we just talked about, then the system will pick KNN. And also, if we think we made a mistake, we think we have index, and we want to use ANN, but not all the conditions are met, then the system can automatically fall back to KNN if possible. One example is that if there's no index, we think that there is a, but somehow we forgot to create. And for example, if we already said approximate distance, but the index does not exist, it will fall into KNN. Or if we happen to specify a different distance measure. Remember, we earlier said the distance measure is a mandatory option when creating index. But if we made a mistake or we want to test some different distance measure, and then we can use a different distance measure that is not the same with the index distance measure, and at that case, Cloud SQL can fall back to KNN as well. So as any other database features, we also have the monitoring points. In this one, the information schema in the InnoDB vector indexes, it's very similar to InnoDB indexes. We can see that we have information about the index name, what table it belongs to, the index type. You can see it's a tree SQ here, the dimension, distance measure, and all the other important characteristics and metrics. For example, number of leaves tells us how many partitions are created through the training process. And num leaves to search explains how many partitions to be searched for any query. And we can see from here, it's a quite small subset of all the data sets. And tree memory is the memory consumption for the index, the in-memory part of the index. And then all vector indexes has more details, not just the loaded index like above, but also those created but not loaded yet. As you can see, the status is pending load, and we have detailed configures. I did not list all of them, but if you have a real index, you can take a quick look yourself. The index vector, InnoDB vector indexes memory gives a quick overview of how the specified vector index memories are allocated and how are they used. And also we have a few global status. It tells us how many KN fallbacks had happened and what are their reasons. So we can use it for debugging purpose and see if we have any glitches or some corner cases missed in the overall application design. Okay, so far, I hope by now you're already excited about the feature and wanted to give it a try. So here are the resources. For test driving, it's quite simple. Just create a MySQL instances in Cloud SQL and turn on the flag. Remember, this feature is only available from version 8.0.36 and above. So pick the right version, whichever you want. And we also have lots of documentations. You can look through the Cloud SQL online documentations. I give a few examples here. The vector search is the entry point for all the vector in related features. And this integration with Vertex AI tells you how to call these user-defined function to get the predictions. And also, if you have any feedbacks, you want to reach out to us, feel free. Don't hesitate. Questions, we'll try our best to answer, or at least find the appropriate person to help with that. And that's it for this talk, and thank you so much for your time.